Hi everybody. In this video, we're going to talk about how to teach your students how to reduce fractions and some visual models that they can use to understand that process. So in our last video, we talked about how fractions are considered equivalent if they represent the same amount. And you can show this with area models like we did here. And when we look at these three fractions that are all equivalent, they're all equal to each other, but this one is considered to be the simplest one because it involves the smallest numbers in the numerator and the denominator. And so 1/2 is the simplified form of 2/4 and 4/8. Similarly, if we look at these equivalent fractions that we showed with a fraction strip model, all of these fractions are equivalent to each other, but 2/3 is the most simple version of these fractions because it has the smallest numbers in the numerator and the denominator. And so the goal of reducing fractions is to take whatever fraction you're given and get it into the simplest form. And so the way that we do this, as I'm sure you're familiar, is you look at the numerator and the denominator of the fraction and you divide by the factor that they have in common. So we say, okay, well, 12 and 18 can both be divided by 6. And what it means when we're dividing 18 by 6 is that we're going to take our 18 pieces in our whole circle and split them into groups of 6. So here's one group of 6, and then here's another group of 6, and here's another group of 6. And when we divide those 18 pieces into groups of 6, we end up with 3 groups altogether. And the 12 pieces that were shaded ended up equaling 2 of those thirds because there's 2 of our new pieces that are shaded. And so this is very similar to like when we were finding equivalent fractions, because when we found equivalent fractions, we multiplied the top and the bottom by the same number. And when we're reducing fractions, we're going to divide the top and the bottom by the same number. So one of the questions your students will likely have is, what number are you supposed to divide by when you're reducing fractions? Do you just choose some random number? Like in the last problem, I chose the number 6, but how did I get that number? So let's take a look at what would happen if we were to divide by any random number. So let's divide by the number 5. Well, if I do 18 divided by 5, that means I'm taking the 18 small pieces in the circle and splitting them up into groups of 5. So here's one group, here's another group, here's another group, and I don't have enough pieces to make my last group of 5. And so this is why we can't just divide by any random number, because we need to have a number that the bottom number or the denominator can be equally divisible by. And in this case, 18 divided by 5 does not equal a whole number. And so we can't just divide by 5. So let's pick another random number that the denominator is divisible by, like let's say the number 9. So if I do 18 divided by 9, this should give me the number 2 or a half when I do the division. And if we look at it, that does work out that way because we have 3, 4, 5, 6, 7, 8, 9 pieces. And when we group them together, that makes a half. And when I take the remaining 9 pieces and group them together, that makes another half. So that part works out fine because we have 18 pieces and we can divide them equally into groups of 9. However, when I do 12 divided by 9, I don't get a whole number because I have one full half that's shaded, but then I have part of the half that's shaded on the other side. And so 12 divided by 9 doesn't give us a whole number, and so that isn't useful for reducing fractions. And visualizations like this are one way that you can show students that you're going to reduce by numbers that both the numerator and the denominator can be divided equally by. So let's take a look at a number other than 6 that still meets this requirement. So let's say your students were to look at the numerator and denominator and say, okay, well, they're both divisible by 2 because they're both even numbers. Well, that basically means that you're grouping these together into groups of 2. And if I do that, 18 divided by 2 equals 9. So I should get 9 of these pieces in the circle all together, and it looks like I will get that. So that tells me that 12/18 is equivalent to 6/9, which is a true statement. Those are equivalent to each other. However, this isn't fully reduced because 6 and 9 are both divisible by 3. So I can further reduce this by dividing the numerator and denominator by 3, which basically means I'm going to take 3 of my 9 and combine those together, take my other 3/9 and combine those together, and these 3/9 and combine those together, which gives me the fully reduced fraction of 2/3. And you can tell your students that you know that it's fully reduced when the numerator and the denominator do not have anything in common that they can be divisible by or divided by. So that's how you can show your students what numbers they can divide by when they're reducing fractions. And after they have some practice with this, they may notice that some numbers are easier to divide by than others. Like in this case, we divided by 2, but then we had to divide by 3 because the resulting fraction wasn't fully reduced. But in this example, when we just divided by 6, we got directly to the reduced answer. And so once your students are noticing that, you can teach them about the greatest common factor to help them know what number is the most efficient to divide by. Because you can divide by 2 or 3 or 6 when you're reducing this fraction, but it's more efficient to divide by the number 6. And the way that you find that number is by finding the greatest common factor of the numerator and the denominator. So if we list out all of the factors of the number 12, we know that 1 times 12 equals 12, 2 times 6 equals 12, 3 times 4 equals 12, and those are all of the factors of the number 12. Similarly, for the number 18, you have 1 times 18, 2 times 9, 3 times 6, and you can't divide 18 by 4 or 5, and so those are all of the factors of the number 18. And when we look at the factors of these two numbers, the biggest one that they have in common is the number 6, and that's the number that's the most efficient to divide by. You can divide by any of their common factors, like 2 or 3, or technically even 1, but that wouldn't really help you reduce it at all. So you can always divide by any of the factors they have in common, but if you divide by the greatest common factor, that will be the most efficient. So you can also reduce fractions similar to how we found equivalent fractions on a number line. So if we had 21/14, that would represent this point right here. And because 21 and 14 can both be divided by 7, we could divide the top and the bottom by 7. And the way that this would look on a number line is that we're going to split the 14ths up into groups of 7. So I have 1, 2, 3, 4, 5, 6, 7. So I'm going to group all of those together. And then I'll go 1, 2, 3, 4, 5, 6, 7, and group all of those together. And 1, 2, 3, 4, 5, 6, 7, group all of those together. And just to complete my number line, I'll go ahead and do this one as well. So I have 1, 2, 3, 4, 5, 6, 7, and we've got that. Okay, so when I divide those, notice that the denominator of the reduced fraction is going to be 2 because the distance between 0 and 1 has 2 of those grouped together units. And same thing with the distance between 1 and 2. You have 2 of those squished together units that have 7/14 within them. So that's where we get the half on the bottom. And then we just look at how many of those units does it take to get to this point that's equivalent to 21/14. So we just count, and there's 1, 2, 3 of those units. And so that means that 21/14 is equal to 3 halves. And that's how you can use a visual number line model to help your students reduce fractions. So if you have any questions, let me know, and I hope you have a great day.